Okay guys, so we are going to be looking at percent ionization, and this is another application we'll see to help us look at how much of a particular acid or base ionizes, and this can give us clues to our equilibrium values that are in our ice tables, as well as being able to help us find Ka and Kb if necessary. So percent ionization is very similar to other percentages that you may have seen in math and things. It looks at the percent of the ions produced out of, or I should say the concentration of the ions produced compared to the concentration of the parent acid or base times 100 to make a percentage. So if we're dealing with an acid, we're doing the hydrogen ion concentration over the acid concentration times 100. If it is a base, we're doing the hydroxide ion concentration over the base concentration times 100. And note that for the hydrogen ion concentrations in hydroxide, this is the equilibrium amount. So in our ice table, it's what is in that last row, whereas the acid and base amounts are the initial amounts, so our beginning amounts, and we're looking at how much of them break up and split up overall. So the amount of ionization that occurs depends on that initial concentration. And in general, the more dilute a solution is initially, the greater the percent ionization. Because if it is more dilute, there's going to be more ions produced overall, essentially. So the more acid concentration we have, the higher the amount of hydrogen ions produced typically. So higher molarities tend to produce more ions overall. So let's look at how this is actually going to work. So here it says to calculate the pH and percent ionization of a 0.050 molar solution of hydrocyanic acid. So this is a question that we would need the Ka value for, and that's typically given. So our Ka value here is 6.2 times 10 to the negative 10th. See, again, that would be provided, or that's something that you would be able to look up in your textbook. So here, hydrocyanic acid is a weak acid. So weak acids, remember, are Bronsted-Lowry acids, so they react in water. And in water, the acid gives up a hydrogen, so it's going to produce the cyanide ion and then the hydronium ions. For us, it tells us that initially we are starting with 0.050 hydrocyanic acid. Remember, we ignore water. We have none of our ions initially. We don't know how much of this ionizes. So we know since our products are 0, they will increase by a factor of X. And our reactant will decrease by a factor of X. And those can plug into Ka just like we've done with other weak acids. So our Ka was 6.2 times 10 to the negative 10th. That would be equal to our products, or X times X. So that would end up being X squared. Over, we have the 0.050 minus X. We can ignore X here because our concentration would be to the negative 2nd power, and our K value is to the negative 10th. So we would multiply by the 0.050 and then take the square root. And here we would get that our X value is equal to 5.6 times 10 to the negative 6th molar. and that is equal to our hydronium ion concentration from our ice table. So addressing the question, it does want to know the pH of this substance. So that's like what we did the other day. So pH is the negative log of H plus. So we can plug in the 5.6 times 10 to the negative 6th. That would give us a pH value, and it should have 2 decimal points. So this would be a pH of 5.25. The second part of the question wants to know the percent ionization of this. So we said percent ionization, you take the concentration, since this is an acid, the concentration of the hydrogen ion or the hydronium ion, which we said was X, which was 5.6 times 10 to the negative 6th, over the concentration of our original acid, the 0.050 molar. That then gets multiplied by 100 to make a percentage for percent ionization. So, and we will leave it at 2 sig figs to match up. So this would be a percent ionization of 0.011% ionization. So that tells us how much of that original acid actually became ions and actually separated overall. Another way that we're going to see these, here we have methylamine, which it tells us is CH3NH2 is a weak base. So pay attention that it is a base. It says in 0.100 molar methylamine, only 6.4% of the base has undergone ionization. And this wants to know what is the Kb and pKb values for methylamine. I'm going to introduce pKb. We will use that later on with some of our buffers and stuff like that. But it's very similar to pH, where it's the negative log of H. That is instead going to be the negative log of Kb. But we will come to that in a second. This one is a little backwards from the last one that we did, where this one, it tells us the percent ionization, and we have the original concentration of the acid. So we can do that percent ionization formula first to figure out how much of the ions are produced. So if we do the 6.4% ionization, we do not know the concentration of, since it's a base, it will be hydroxide. And our concentration of our base is 0.100 molar. And of course, it's times 100 to make it a percentage. So if we solve this for hydroxide, this is going to have a hydroxide ion concentration of 0.0064 molar. So this, remember, is the amount at equilibrium. So we can utilize that in an ice table to find all of our equilibrium values, because remember, we need equilibrium values to find Kb. So we can set up an ice table with our methylamine, the CH3NH2, and that goes in water. And remember, since this is a base, it is accepting a hydrogen, so that will form CH3NH3 plus and hydroxide. Sorry, I'm trying to squeeze it in there. So it told us our methylamine we started with was 0.100 molar. We're ignoring water because it's a pure liquid. And we found that the equilibrium amount for hydroxide was 0.0064 molar. And initially we would have none of these ions. So hydroxide increased by 0.0064, which means the methylamine ion that it changed into would also increase by 0.0064. And our reactant would decrease by 0.0064. So that would end up being 0.0936. And yet again, I don't want to round until the very end because it can skew our answer. So now that we have all of our equilibrium amounts, we can find KB. So that would be our products. So we have 0.0064 times itself, so we can just put squared, over 0.0936. So this would have a KB value equal to 4.38 times 10 to the negative fourth. You probably could have done just 4.4, but our original number had 3 sig figs, so I left it at 3 sig figs. That's one where they would probably not be too picky on based off of your other data. And like I said, if we want PKB, PKB is just the negative log of KB. So if we do the negative log of the 4.38 times 10 to the negative fourth, we get that the PKB value here is equal to 3.36. So that is how percent ionization can be used a couple of different ways. You may have questions presented this way where you can use that percent ionization to figure out the equilibrium concentrations, or if you have the equilibrium concentrations, you can utilize that to find the percent ionization.